All right, let's get into it. We're about to crack open one of the biggest cold cases in history. The victim, a totally lifeless planet. And the mystery, how, over 4 billion years, it somehow gave rise to, well, to us. This is the story of where life itself came from.
So that's the big question, right? How does life just start on a world where there's nothing? It's a question that scientists have been wrestling with for centuries, and we're finally starting to piece together some really compelling clues. So where do we start an investigation this old? We go to the scene of the crime.
I want you to forget everything you know about our nice blue-green planet. Early Earth was something else. It was a hostile alien world. Imagine volcanoes constantly erupting, asteroids and comets slamming into the surface all the time, and an atmosphere you definitely couldn't breathe, thick with methane and sulfur, but with almost zero oxygen. Yeah, not exactly a vacation spot.
So to even begin to solve this mystery, we have to understand the crime scene. The conditions on this hostile early planet weren't just a backdrop to the story, they were a key player, setting all the rules for how life could possibly get started in the first place. So in this chaotic, unwelcoming world, how did that first flicker of life actually ignite? This is where we start looking at the first clues. Scientists, have a pretty solid list of suspects for what could have provided that initial spark. So, scientists pretty much agree on the basic recipe for life. First, you need a steady source of energy. Think lightning, the sun's radiation, or heat coming up from inside the planet. Second, you need organic compounds, the carbon-based molecules that are life's building blocks. And third, you absolutely need liquid water, the ultimate solvent where all the chemistry can actually happen.
Okay, but having all the ingredients in one place is one thing. How do they come together in just the right way to create something as mind-blowing as a molecule that could copy itself? This is where the debate gets really interesting, and we've got two main theories about where life's first laboratory was located. So on one side, you have the famous primordial soup theory. The idea here is that life got started in shallow, sun-warmed ponds on volcanic islands. The energy came from lightning strikes and harsh UV radiation. As water evaporated, all the chemicals got more and more concentrated, which made it more likely they'd react. Then, on the other side, you have the deep-sea hydrothermal vents. These are like strange, rocky chimneys on the ocean floor, just pumping out hot, mineral-rich water. Here, the energy comes from the planet's internal heat and the wild chemical differences between the vent fluid and the cold ocean water around it, basically creating a perfect natural reactor. And trust me, this is a huge debate in the scientific community. As biochemist Nick Lane from University College London points out, a big question for the shallow pool idea is, what was the continuous driving force? Hydrothermal vents, on the other hand, have this constant flow of energy and chemicals. And this is what's so great about science, right? It's all about challenging each other's ideas to get closer to the truth.
But what if the key ingredients, or maybe even the spark itself, didn't come from Earth at all? There was a famous meteorite, the Murchison meteorite, that fell in Australia back in 1969. When scientists studied it, they found it was packed with dozens of different amino acids, the building blocks of proteins. This opens up a wild third possibility. What if life's ingredients were delivered from outer space?
All of this incredible detective work has a name. It's a field called prebiotic chemistry. It is basically the ultimate forensic science. It's all about piecing together that exact chain of chemical events that bridge the enormous gap between simple, non-living molecules and the very first primitive forms of life.
Okay, so we've got our potential crime scenes and the key ingredients. But how did a bunch of random chemicals assemble themselves into something as organized and elegant as a living cell? That's the next massive piece of the puzzle.
The absolute game changer here is replication. To be alive, you have to be able to make copies of yourself. But this creates a classic chicken and egg problem. DNA holds the blueprint for life, right? But it needs proteins to do any of its work. And proteins are built using the blueprint from DNA. So which came first? The leading theory is something called the RNA world hypothesis. It suggests that a simpler molecule, RNA, came first because it can do both jobs. It can store information like DNA, and it can act like a protein to get things done. A real molecular Swiss Army knife.
From there, you start to see the first key structures of life coming together. First up, fatty acids form these simple bubbles, creating protocells. These were just tiny little containers that separated the special chemistry of life from the chaos of the outside world. Inside, ancient RNA molecules evolved into the ribosome, the protein-building factory that's still at the heart of every single one of your cells today.
And finally, in what might be the greatest team-up in history, microbes started living inside other microbes. This eventually led to complex cells with specialized parts, like the mitochondria that are powering your body right now as you watch this.
So for billions of years, life stayed small. It was just microscopic, a very slow, very quiet start. But then, something truly extraordinary happened. The investigation takes a dramatic turn as life suddenly bursts onto the scene in a riot of new and complex forms. Let's just try to get the scale of this right. For more than 80% of life's entire history on this planet, that's over 3 billion years, it was all just single-celled organisms, little microbes floating around in the oceans. Then, in what is basically a geological blink of an eye, the world just exploded with large, complex animals. It was an absolute explosion of diversity. This timeline really puts it all into perspective. Just look at this. The first evidence of microbes is way back at 3.7 billion years ago. But look how long it takes to get to the first simple animals, like a sponge, at 800 million years ago. That gap is just immense. Life was incredibly patient. A huge turning point was the Great Oxidation Event, when tiny cyanobacteria started pumping oxygen into the atmosphere. This totally changed the planet and, well, it paved the way for complex, oxygen-breathing life to evolve. I mean, the Cambrian explosion was a biological revolution. For the first time, we see fossils with hard parts, shells, spines, skeletons. Animals got active, developing heads and tails to move with purpose, and brand new ecological roles appeared, like active predators hunting other animals. It was a completely different world. And by the end of it, the basic body plans for nearly every animal group that exists today had been established. Just incredible. So, after conquering the oceans, life was about to take its next giant leap. The next phase of our story is the colonization of a whole new world, the harsh, empty continents. Think about it. Surviving on land presents a whole new set of brutal challenges. You have to figure out how to breathe air instead of water. You have to deal with gravity without the support of buoyancy. And you have to find a way to avoid drying out in the sun. It was a hostile environment, but the prize was immense, a vast untapped frontier. And this didn't happen all at once. It was a step-by-step invasion. First, the plants got there, around 470 million years ago. They were the true pioneers. They literally created soil, changed the atmosphere, and laid the groundwork for everything else. Then, about 40 million years later, the first animals followed, arthropods, like ancient centipedes and scorpions. And finally, our own ancestors, the lobe-finned fish, evolved their fins into limbs and made the final leap onto land. So, we followed this epic 4 billion year trail of evidence, from the first molecules to microbes to us. But the clues didn't just stop in the past. Our investigation is going to end with a really surprising modern twist, where the very blueprint of life, DNA, has become the ultimate tool in modern crime solving. Here's a number for you, 1,000. That's roughly how many skin cells you shed from every single square centimeter of your body, every hour of every day. That's kind of gross, but it adds up to billions of cells a day. And every single one of those cells contains your unique DNA blueprint, a direct, unbroken link stretching all the way back 4 billion years to those first self-replicating molecules. All of us are constantly leaving behind an invisible trail of our own genetic history. Our DNA settles into the dust of every room we enter. It's even floating in the air around us. And just like paleontologists hunting for ancient fossils, modern forensic investigators can now collect this dust DNA as evidence. It has become the ultimate invisible witness, proving someone was at a crime scene without fingerprints or any other kind of traditional trace. From the primordial soup to the DNA and dust, the story of life is really a story of clues being left behind. The investigation into our own origins is the oldest, coldest case of them all. And it really makes you wonder, as our scientific tools get sharper and more powerful, what other invisible witnesses and hidden clues are still out there, just waiting to be found?